Thank you. So yes, I'm Bruce Grove. Mentioned jet engines in my bio. It's actually where I started. So many people may know the Wright brothers. Wright brothers were famous for heavier-than-air flight. They were the first people at Kitty Hawk to actually have a self-powered aircraft take off and fly a distance. And it led to what we know today as the aircraft industry, that incredible ability to travel great long distances. But it came about through a series of people really sort of building the pieces, the fundamentals of the technology to make that. 20 years before they flew at Kitty Hawk, a Russian named Alexander Majesky, almost nobody will have heard of, and yet he flew an aircraft heavier than air for 100 meters. The reason it wasn't considered to be the first powered flight, it was an assisted takeoff. He went down a ski jump and he actually took off, but they've subsequently proven that had the other pieces of technology been there, specifically the engine, the plane could have actually sustained powered flight by itself. So one of the things we have to think about is when we're building platforms, when we're building solutions, we need lots of pieces to come together to actually turn it into something viable from a technology perspective. So the 3 steps piece of this is also why no one talks about massive scale. Why do people not talk about the number of concurrent users in things like cloud gaming? So a decade ago, a lot of companies were involved in the cloud gaming race. Those companies have all pretty much come and gone. Now, one of those companies, OnLive, back in 2007 in Silicon Valley, I was the first head of engineering for. I have a lot of experience in cloud gaming. I designed the servers, I worked on their clients, I worked across the engineering team to build something that really set a stage for can we deliver games at scale. And lots of people said it can't be done. We can't stream games from the cloud. They'd say latency, they'd say bandwidth, they'd say any kind of number of excuses why it couldn't be done. But it worked, and it worked very well if people were close enough to the data centers, if people had a decent internet connection, if they could connect to the servers. So all of those companies went away, and then here we are, a decade later, and it all feels very familiar. All of these companies that we have suddenly seen coming up talking about cloud gaming are talking about all of these great things they've overcome. But have they really actually done anything differently? Are they really doing something that has moved the technology forward? Or are they still going down the ski jump? And are they still doing their power-assisted takeoff? So how do you do cloud gaming? Well, the problem is how you build it. You have to take all of these pieces of infrastructure, all of these pieces of architecture, you have to take all of these game machines and put them in the cloud, and then you have to take lots of users and get them all to connect together. And all of those moving parts lead to a problem of how does it work at scale. Although you can stream games, we're still doing the same thing we were doing a decade ago. We're moving our machines around, and we're just changing where we actually get that resource from. We're not actually changing the way we do it. So this is still a power-assisted problem. We do this for everything. We talk about virtual desktops. We want to make our virtual desktops more powerful. How do we run huge CAD applications? How do we actually design our games in the cloud? Why do I need a big workstation under my desk to do that? Why do I want to build a bridge when I want to use the power of the cloud to build ever bigger models? Automotive. Corvette launched a car configurator recently. It's a beautiful thing. It uses 3D Unreal Engine technology to give you the most photorealistic version of a car you've ever seen. But it is incredibly expensive to operate, and when they launched it, they ran out of Amazon servers to have people use it. And that's a car configurator. That's not 10 million people playing Fortnite. That was actually about 6,000 people trying to build their Corvette at the same time. And then we have training, simulation, any number of uses for 3D. And they're all chasing this resource that we keep putting into the cloud that's really expensive, the graphics processor itself. So the elephant in the room continues to be that we're still using a ski jump to actually build this technology. Well, so what do I mean by that? Well, before the cloud, we have a CPU, we have a graphics processor, we render our image on our screen, and we get a lovely representation. We get beautiful games, we get beautiful graphics. Now, this is the same if I use a phone, it's the same if I use a game console, and they keep getting more and more powerful. With pixel streaming, what we see today from Stadia is the same thing we saw 10 years ago from OnLive. I put the CPU and the GPU in the cloud. I then encode it into video. And then I deliver that video down to your screen. Now, in doing that, I actually compress it. That's the nature of video compression. So the image I put on the screen is not the same image I started with at my graphics processor. The very nature of it means it's a compromised solution. But it also means that every player needs the same equivalent resource that they used to have before the cloud. If I wanted 10 million people to play Fortnite, I would need 10 million of those equivalent consoles in the cloud, close enough to the users, all with good enough network connections, all to connect, just so that I can run that single game with that number of concurrent users. League of Legends just broke 3.5 million concurrents a couple of weeks ago. PUBG broke 1 million several years ago. The number of concurrent users in these games now is massive. So if we're really to fulfill cloud gaming, we need a solution that's actually going to scale for that. So Polystream created something called command streaming. We thought about the problem differently. We looked at the fact that our compute resources should be distributed. Our compute resources should be on demand where we need them, when we need them. We shouldn't just be moving all the compute from one place to another. We've all got phones in our pockets with graphics processors on them. We all have laptops, we have tablets, we have PCs or Macs. So rather than just push everything from one place to another, Polystream orchestrates the resources. It looks at what you need when you need it. And so what we do is we run the game in the cloud, the application, we run that on the CPUs, and we then take the commands, the graphical commands, and we stream them to your graphics processor. One of the benefits of that is you're drawing locally. It's pixel perfect. It is, by its very nature, no longer compressed video. It is actually locally rendered graphics. It also means what we're using in the cloud is CPU. CPU is a very, very easy to get resource. It's very elastic. There's a lot of it. There are literally billions of CPUs in the cloud. So suddenly, the idea that we could run 10 million, 20 million, 50 million isn't so far-fetched. And in fact, to prove that, just in December, we ran 40,000 concurrent users. Now, we know that none of those other platforms I previously mentioned have even come close to that yet. Not even the largest names on that list have come close to running 40,000 concurrent users. 40,000 is still a relatively small number compared to Fortnite. We're still in development, so we stopped there just because it was a test, it was a trial. But if we can do 40,000, there's no reason we can't do 400,000 or 4 million. So that's command streaming today. So our 3 steps really are, we've had pixel streaming. There's our ski jump assisted takeoff. Command streaming demonstrates there's a better way to deliver 3D applications from the cloud. There's a way that scales. There's a way that uses elastic general purpose resources. But where the internet is going, where the network is going, is something called composable compute. Composable compute is using all of the resources. It's thinking about where each piece is that we need when we need it. No longer just running a game from a GPU in a cloud and then just trying to get it over there using a brute force approach. But it's actually looking at all of the resources. 5G is about low latency networks. It's also about massive numbers of users connecting to those networks at the same time, and that's very important. It's not really about faster pipes. It's about connectivity. It's about low latency. CDNs are a place where we can put assets. They're a place where we can cache parts of it. Edge compute is where we talk about today is where we just kind of route packets for the last mile. It's the last piece of internet, and it's not particularly clever. It's not particularly interesting. But actually, edge compute could be a lot smarter. There are pieces we could offload there. And then at the bottom, we have your machines. We have whatever we're connecting to. We have no reason not to use that compute. The old saying, throw the baby out with the bathwater, that's what cloud gaming has been. It has been take that machine and just push it all to one side and expect everyone to jump onto it. But instead, what we're actually doing is ignoring all of the compute and the resources that are available elsewhere. And we want to use those resources because that's how we make more efficient compute. That's how we make more scalable compute. And that's ultimately how we stop Corvette from falling over at 6,000 concurrent users, or Fortnite falling over at 15 million concurrent users. We want them all to be able to access resources when they need them and where they need them. So it means we can scale. Here we are, Polystream's already there. Polystream now has no reason to not keep scaling. Around the world, there's more than 550 hyperscale data centers. The important thing about those data centers is they have ubiquitous compute in them. They have the kind of compute that can run a game. We could run a game out of any data center in the world today using Polystream's technology. And if you take the locations of those 550 data centers as they are today, it means you're also close to users, which means that I can always overcome latency just simply by being closer to the end users, being where I need them when I need them. And it's those recurring themes that are about putting the compute where you need it, when you need it. That's how you make it scale. That's how you make it operationally effective. That's how you make businesses that can operate a cloud gaming service. So, 3D interactive content, an apps-ready world. Doesn't matter whether it's car configurator, 3D retail, doesn't matter whether it's games. It is about bringing all of these devices together, orchestrating the needs for them, and making them all work seamlessly so that those resources can give every user the best possible experience regardless of their device and regardless of where they are in the world. We just don't believe it will be using video and GPUs in the cloud. Not like that. Thank you.
Thank you, Bruce. Do we have questions?
Thanks. If you're computing the game in the cloud, but then you're rendering the graphics locally,
Yep.
what kind of games are going to work well and look good, and what games aren't? If my local GPU power is fairly limited, then surely you've got a lot of variation in what different users will see.
Yes. So today we've taken this approach to compute that the local machine is there to run the game. So if you have a GPU and a CPU, the CPU is there to power the graphics processor. And in doing that, our assumption is always that I'm going to have a low-powered graphics processor if I have a low-powered machine. Whereas if we start to look forward and we think about what does it mean to build those next infrastructures, what does our architecture look like? There's no reason for me not to have a streamer box with a better graphics processor in it. It's still a cheap box, but it could render 4K and it can render it beautifully. And today I'm stuck with this problem that if I put a big GPU in it, I must put a big CPU in it. And it's about rethinking not just sort of how do I get the application, but what is the end user's needs? If I want a next generation console, do I really need to put a 10 terabyte disk in it? Do I really need to put 16 or 32 gigabytes of RAM in it? If all I actually need is enough storage, enough compute, and a nice graphics processor, and suddenly I can give a great experience. And that's as true of a point of sale terminal or a laptop or any other device. My phone has a 4K graphics processor in it, but actually doing 4K on my phone is kind of over the top sometimes. So it's about rethinking the balance of the entire infrastructure such that they're all appropriate for their needs. If I want a gaming machine, if I want a streaming gaming box, maybe it doesn't need to have as much compute in it, because what I really want to do is be able to say, I always want to draw a great image, but in the cloud, I might want to build an open world with 1 million players in it. And I'm not going to be able to do that with the amount of netcode I would have to move backwards and forwards today. So it's about rethinking that and then building the applications that fit in that world.